Okay, today we're talking about the wave-particle duality, and what led to this is what we talked about in a previous video, which is that classical theory broke down when trying to explain energy and matter and how they were so different. So instead, what we now have is the idea that waves and particles are not distinct things, but that there is a continuum of waves and particles. And so that energy, which was previously thought of as a wave, and light, which is also a wave, have particle qualities. Okay, and we talked about the fact that we now call particles of light photons. Okay, well, and if that is true, there's a guy named Debroglie who came along and said, well, if that's true, then the opposite must be true, in that matter must have wave-like qualities. Okay, if energy behaves like a particle, then matter must also behave like a wave. And so he came up with this equation, which is basically a result of combining E equals mc squared, which is the classic equation relating energy and matter, and the fact that E equals h nu, which we talked about, that energy equals a constant h times frequency, and the equation that relates the speed of light to frequency and wavelength. And he combined them and came up, and he changed the speed of light to just a v for velocity, because he was talking about matter, and the speed of matter will no longer be the speed of light, but it's just going to be a speed. Okay, so he came up with this equation, which is known as the Debroglie Equation, which says that the wavelength of light is equal to a constant, which is Planck's constant, divided by the mass of the object times the velocity of the object. Okay, so h is known as Planck's constant, and is equal to 6.636 times 10 to the minus 34 kilogram meters squared per second. All right, so that is Planck's constant, h. Anyway, it gives us this Debroglie equation, which then allows us to calculate the wavelength, lambda, of any object that is moving, that has a mass and a velocity. So, all moving matter has a wavelength. Okay, so why don't we notice this? Why don't we notice there being a wave-like quality, to matter? And the reason is that if you use this equation for ordinary objects, you'll find that it's immeasurable. Okay, so let's say like you throw a ball. You'll calculate the wavelength of that ball moving through space as 10 to the minus 34 meters for a wavelength. And that's just way too tiny for us to even see or measure. So we never notice that ordinary objects are actually smeared out a little bit, and they have a wave-like qualities. However, it turns out that electrons are small enough and fast enough that we do see that they have wave-like qualities. Electrons are very small, and they can move very fast, and they do show diffraction patterns. Remember, we said diffraction was a quality usually assigned to waves. So electrons display diffraction patterns, and that is measurable. So now we realize that electrons are really smeared out. They're not in a particular location, but they have wave-like qualities, which means they're smeared out. All right, so the fact that electrons are smeared out and don't have a precise location directly led to the Heisenberg uncertainty principle. Okay, this is the equation for the Heisenberg uncertainty principle. And let me tell you about the parts. Okay, first of all, delta in this case does not mean change in, it means uncertainty in. So it's a slightly different meaning of delta. And x is the position of something, whatever object you are talking about. And m times v is momentum. Okay, so, and there's a inequality here, greater than or equal to. So the uncertainty in the position times the uncertainty in the momentum of an object is greater than or equal to Planck's constant divided by 4 pi. So what that means is that because it's an inequality, we can't know the position and the momentum of an object at the same time. So we can't know the position and the momentum of an object at the same time, at least not precisely. Okay, so if the uncertainty in position is great, then the uncertainty in the momentum might be smaller, but you can't know both at the same time. And this plays out in electrons in atoms where you might know the momentum of the electron, but you won't know its position exactly. It's smeared out. Okay, I have a problem for you to try now. Which of the following would have the greatest de Broglie wavelength if they had the same velocity? So stop the video and think about that. All right, we have a proton, a baseball, and an electron. What is the equation for the de Broglie wavelength? It is lambda equals Planck's constant over the mass times the volume. Oh, sorry, not the volume, the velocity. So we look at these three, and we see that the mass is inversely proportional to wavelength. So the thing that will have the greatest wavelength will be the thing with the smallest mass, and that would be an electron. Okay, next we will deal with the quantum mechanical model of the atom. All right, so I've shown an equation here that I don't expect you to understand in detail, but we do want to explain the quantum mechanical model at this point, since we said the classical theory breaks down for the atom, so we need to use a quantum mechanical model. And this is known as the Schrodinger Equation here, and it's a very simple form. This H with the hat on it is known as the Hamiltonian operator. And it actually is a series of very complicated equations. It's not simple at all. I can't do it. Okay. And E, this value E, are the energy levels of the atom, which are discrete. And then you have psi. Okay, psi is given down here. Psi is known as an orbital. Okay, it is also known as a wave function. And when we solve the Schrodinger equation, we get the wave functions, which are essentially where the electrons are, and we get the energy levels, the E's. All right, and the wave function, as I just sort of said, tells the position of the electrons in the atom. Okay, but it doesn't have a very good physical description, so we usually talk about psi squared, and this is a Greek letter psi, which is the probability of finding an electron in a certain location. All right, and if we do solve this equation, the Schrodinger equation, for one electron systems, like the hydrogen atom, we do get the Rydberg equation, which gives us information about the hydrogen atom. But for all other systems with more than one electron, this equation is much, much more complicated.